Our planet looks peaceful from space, but beneath the surface, Earth is alive with constant motion. Sometimes this movement erupts in a sudden, violent event, an earthquake. An earthquake is the shaking of the ground caused by a rapid release of energy in the Earth's crust. Think of snapping a twig. Energy builds up, then releases in an instant. Earthquakes work the same way, but on a massive scale. These events remind us that the ground beneath us is not as stable as it seems. Earthquakes can reshape landscapes, topple cities, and alter history in seconds. Understanding earthquakes is crucial for survival, not just curiosity. By studying them, we learn to build safer structures and prepare for the inevitable. Scientists use technology to detect, measure, and warn us about earthquakes, sometimes giving us precious seconds to act. In this journey, we'll explore what causes earthquakes, where they strike, and how we measure and respond to them. We'll visit seismic hotspots like Japan and Indonesia and see how science helps us coexist with our restless planet. Earthquakes are a story of immense forces and human resilience. Let's uncover the secrets beneath our feet. Earthquakes begin with the structure of our planet, the lithosphere, broken into tectonic plates. These plates slowly drift atop the mantle, colliding, sliding, and grinding against each other. Their boundaries, called fault lines, are where most earthquakes originate. As plates move, friction causes them to stick, building up strain over years or centuries. When the stress becomes too great, the rocks snap, releasing energy as an earthquake. The rupture starts deep underground at the hypocenter, with the epicenter directly above on the surface. Seismic waves radiate outward, shaking the ground most violently near the epicenter. This process is explained by the elastic rebound theory. Rocks bend, store energy, then suddenly snap back. The abrupt slip can move the ground by centimeters or meters in seconds. Aftershocks often follow as the crust continues to adjust. These smaller quakes can last for weeks or months, posing ongoing risks. Understanding these mechanics helps us predict where earthquakes are likely to strike. The restless movement of tectonic plates is the engine behind every earthquake. Earthquakes cluster along tectonic plate boundaries, not randomly across the globe. The Pacific Ring of Fire is the most active zone, home to 75% of the world's volcanoes and frequent powerful quakes. Japan sits at the intersection of 4 major plates, making it one of the most earthquake-prone countries. The Japanese have adapted with advanced engineering and a culture of preparedness. Indonesia, another hotspot, lies on a subduction zone where one plate dives beneath another, fueling both earthquakes and volcanoes. Catastrophic events like the 2004 Indian Ocean tsunami remind us of the risks in these regions. In contrast, Australia, located in the middle of a plate, experiences fewer and weaker quakes, but is not immune. Even stable regions can suffer damaging intraplate earthquakes, as seen in the 1989 Newcastle event. No place on Earth is entirely safe from the planet's shifting crust. Today, scientists use seismographs to detect and record even the faintest tremors. A seismograph works by suspending a weight that stays still while the ground moves, tracing the motion onto paper or digital records. The resulting seismogram is a visual record of the earthquake's vibrations. Modern seismographs are highly sensitive, detecting quakes from across the globe. Networks of these instruments allow scientists to monitor seismic activity in real time. When an earthquake occurs, it sends out seismic waves, each with unique speeds and effects. The seismogram reveals when and where the quake happened, how deep it was, and how much energy it released. This data is vital for understanding earthquakes and improving safety. Seismographs are our window into the restless Earth. Earthquakes generate several types of seismic waves, each with distinct effects. P waves, or primary waves, are the fastest, compressing and expanding the ground like sound waves. They arrive first, causing a quick jolt. S waves, or secondary waves, follow, moving the ground side to side or up and down and causing more damage. S waves can only travel through solids, revealing the Earth's internal structure. The most destructive are surface waves, which travel along the Earth's exterior. Love waves move the ground horizontally, shaking buildings from side to side. Rayleigh waves roll the ground in a wave-like motion, both up and down and side to side. Surface waves arrive last, but cause the most intense and prolonged shaking. The combination of Love and Rayleigh waves is what people feel most during a major quake. These waves can topple buildings and reshape landscapes. The sequence and strength of these waves are recorded by seismographs, helping scientists analyze each event. Understanding seismic waves is key to earthquake science and safety. The ground's movement tells the story of the quake's power. Every tremor is a message from deep within the earth. Locating an earthquake's epicenter is crucial for emergency response. Scientists use seismographs to compare the arrival times of P waves and S waves. The time gap between these waves, the SP interval, reveals the distance to the epicenter. One station gives a distance but not a direction. The epicenter could be anywhere on a circle around the station. By using data from at least 3 stations, scientists draw overlapping circles. The point where all circles intersect pinpoints the epicenter. This method, called triangulation, is now automated and rapid. Accurate epicenter location helps direct aid and assess risk quickly. Technology has turned earthquake detection into a matter of minutes. After locating an earthquake, scientists measure its magnitude, the energy released at the source. The Richter scale, developed in 1935, is logarithmic. Each whole number increase means 10 times more shaking and about 32 times more energy. A magnitude 7 quake is vastly more powerful than a 5. The Richter scale allows us to compare tiny tremors and city-leveling disasters on the same scale. Magnitude is calculated from the largest seismic wave, adjusted for distance from the epicenter. The 2011 Tohoku earthquake in Japan, at magnitude 9.1, released energy equivalent to thousands of atomic bombs. The Richter scale tells us the quake's true power, but not its impact on people. The Richter scale measures energy, but what about the human experience? The modified Mercalli intensity, MMI scale, rates the effects of shaking from I, not felt, to Twatzen, total destruction. Intensity varies by location, strongest near the epicenter, weaker farther away. Local ground conditions can amplify or dampen shaking. The 2011 Tohoku quake had extreme intensity near the epicenter, but the tsunami caused the greatest devastation. The 1989 Newcastle quake, though moderate in magnitude, caused severe damage due to local vulnerability. Both scales are essential. Magnitude shows the quake's size, intensity reveals its real-world impact. Together, they guide engineers, planners, and emergency services. Understanding both helps us build safer communities on our ever-moving planet.